Today we're going to talk about evaluating Lewis structures instead of just drawing them or adding a new layer to just the drawing. To start off, I wanted to talk about carbon dioxide. So maybe if you want to pause and draw a Lewis dot structure on your own just to check, you can, but I'm going to get started. There are 4 valence electrons on the carbon. There's 6 for each oxygen. That's a total of 16 electrons for our system. I'm going to quickly draw our carbon and our oxygen. And then we're going to start off just as we usually do, making single bonds, making double bonds as we need to, and then cleaning it up. Now that's all well and good, but just hear me out on this. Our only criterion for a valid Lewis dot structure would be the right number of electrons showing, and we have 16, and 8 electrons associated with each atom. But what if this double bond, these 2 electrons in this double bond, what if instead of having it there, these electrons are clouds, they're probability based, they're a little bit more plastic than we want them to be. What if instead we let those electrons be completely housed on the oxygen on the left? Let me draw that really quick. Now, from a Lewis structure standpoint, that's not a bad structure. Well, it's not a good structure. It's not terrible, but it doesn't really address this carbon here. This is a problem. There's only 6 electrons because we took a shared pair and turned it into an unshared pair. But there's this flexibility. We're allowed to do that. And if we can take a shared pair and turn it into a lone pair, could we hypothetically take a lone pair and turn it into a shared pair? Well, I don't see why not. Right? There's this oxygen here that has all these lone electrons, and if we push them into a bond, what we get is something that looks like this. Now, I mean, this really pushes the envelope of what you might call carbon dioxide, because that does not look the way it looks in most textbooks. I don't like this structure at all. This one doesn't seem to be valid, but this one has 8 electrons associated with every atom, and it's still got the 16 electrons. Hypothetically, I could have also taken that structure and maybe just pulled the electrons in the other direction, pulled them to the right instead. You could imagine that this is another hypothetical Lewis structure of carbon dioxide. And when this happens, when you have multiple possible Lewis structures that are valid, we call the group of them resonance forms, resonance structures of the same molecule. So the idea is that, in reality, these electrons are not dots on a paper. They're clouds, and they interact with each other, and they exist, and they have different densities in different locations. And so these are all hypothetical constructions of what a carbon dioxide molecule might look like at any time. And the truth is, they're all kind of happening, and the electrons are kind of bouncing around. But then why is it that we only really see one when we look in the textbooks and we look it up online? And the reason is formal charge. We talked about the idea of having the right number of valence electrons and a stable configuration around all atoms, but obviously there's multiple present, and it seems like certain things are a better idea or a worse idea. And this really leads into a discussion of what we call electron-rich and electron-poor areas. You can end up with these negative and positive formal charges by following the formula below. I'm going to step through that process talking about the structure of carbon dioxide. Did I do that right? I did do that right. So in each case, we're just going to follow the formula. Let's start by talking about this one on the left. I'm going to number all the atoms. Number 1 here, right? For number 1, oxygen has 6 electrons. We're going to subtract the number of lone pairs. So we've got 1, 2, 3, 4, 5, 6 lone pair electrons minus the number of bonds. So it's got 1 bond. That's going to give us a -1 for a formal charge. This means that compared to an oxygen atom, an unbonded oxygen atom, this oxygen is shown as having more electrons than an atom. That's all that number actually means. For the carbon, we usually have 4 for carbon. We're going to subtract 0 lone pairs, and we have 4 bonds, 1 on the left and 3 on the right. So that's going to give us 0. This carbon has the same number of electrons as it would in an unbonded form. It's a way of saying like how electron dense is it compared to an atom. And then for the third one, this oxygen over here, again, we have 6. We're going to subtract 2 for the 2 lone electrons, and we're going to subtract 3 here for the 3 bonds on this oxygen. And that's going to give us a positive 1. So this one would be labeled with a positive 1, this would be a 0, and this would be a negative 1. Now we could go through and we can do all that math again, but if you look kind of closely, oxygen 7 and oxygen 3 are the same in terms of their electron structure. They both have a triple bond and a lone pair. I'm reasonably sure that if we did the math, we'd get a +1 here as well. I'm pretty sure we'd get a 0 there and we'd get a -1 there. In general, when you have a singly bonded oxygen and 3 lone pairs, that oxygen has a -1 formal charge by the math we see here. Up on the top for 4, 5, and 6, 4 is, we have 6 minus 4 minus 2 is 0, and that's going to apply to that oxygen and that oxygen, and the carbon still has 0 lone pairs and 4 bonds, so that will give you 0. So maybe that would be a bit of a reason why we don't see the bottom 2 structures and we only see the top one in reference to carbon dioxide. It seems like the formal charge is 0 for all of the atoms, and that's in general a good thing. Whenever we have formal charges that aren't 0, especially when you have one side being negative, one side being positive, that doesn't look like a good idea. It seems like one side of your molecule is electron rich and the other side's electron poor for not much reason. Which is nice. I mean, that's a nice way of thinking about it. Let's talk about carbon monoxide, though. This one's fun to draw. We have 4 and 6. We have 10 electrons. So if we draw our carbon and we draw our oxygen, we can start making the bonds like we usually do. We've got a single bond, we got a double. That doesn't work. All right, what we have here is this. You know what? Maybe we could pair those up. I don't know if that would look better or worse. But this carbon has 6 electrons. This oxygen has 8 electrons. So that's good for the oxygen, bad for the carbon. If anything, if we looked at a formal charge, this would be a formal +2 actually. So 4 minus 2 minus 2. Wait, is that? No. Wait, I did that wrong. That's a formal 0. That's fine. This is a formal 0. That's fine. Except this isn't fine. We broke one of our rules. There's not 8 electrons. But you know what we saw before is if we have this pliability of turning lone pairs into bonded pairs, and we push in some from this relatively large oxygen, what we get is something that looks like this. And I am going to bump these into a pair to make it look nicer. Now this is not necessarily pretty in terms of carbon monoxide, but you know what? This has 8 electrons, and this has 8 electrons. Now that said, there's a formal -1 here and a formal +1 here, which is not really great from a standpoint of a formal charge, but this is a good example of showing you this is what happens when you have really reactive species. Right? Carbon monoxide, we know, is terribly poisonous to humans. It does very bad things to hemoglobin. And part of that is because this species is so chemically reactive, because you're constantly in this stability battle between unbalanced electrons and unbalanced formal charges. This allows your electron structure to be stable, but it definitely doesn't put electrons in some sort of a balanced location. It's very lopsided. This is our answer for carbon monoxide. And part of the reason I know that's true is if you add it up, that's 10 electrons. I know of another 10 electron 2 atom system. It's nitrogen. And it turns out that the nitrogen Lewis structure and the carbon monoxide Lewis structure are isoelectronic. It turns like whenever you have a 2 atom 10 electron system, that's the only way to make it stable. So you can use this idea, and we can also fold in something else, and this is going to be like the last point I'm going to make. Polyatomic ions. We glossed over the fact that they're covalently bonded ions, but let's try and draw a couple of them. This one is, in each case, we're just going to take that overall charge, and we're either going to add or subtract from the total. So hydroxide from table E is an OH-, that's 6 plus 1, and then this negative charge means we have another 1, so that's 8. Nitrite is NO2-, that's 5 plus 12 plus 1 because of the negative charge, and that's 17. For ammonium, that's NH4+, so that's going to be 5 plus 4 minus 1 because the plus means we lost an electron, and that gives you 8. And then thiocyanate is SCN-, which would be 6 plus 4 plus 5 plus another 1, and that's 16 electrons. That sounds familiar. So when we try to draw this, and we draw in our atoms with all of their appropriate electrons, what you'll see is you try and make a bond there, and you're kind of done. That's it. You can't really, there's nothing else to work with. This hydroxide is kind of done. Well, that's where that negative charge comes in. You're allowed to add 1 electron where you need to, because we were also only showing 7 electrons until I added that extra dot. So when we clean this up, what we get is a structure that looks like this. And remember that it's a polyatomic ion. For nitrite, same deal, right? We're going to draw our nitrogen. We're going to put it in the middle because it's got the lower electronegativity. And we're going to draw our oxygens as well. And we make our bonds. And what you end up seeing is we can make a double bond there, but again, there's an unpaired electron there. It should be 18, not 17, for those of you who've been yelling at the screen. This extra electron here means we can add it where we need to, and we're going to add an electron there. And that's going to be our structure. Now, in this case, you may have actually wanted to make your double bond on the left, and you can totally do that, and that would be one of those alternate structures for nitrite. This would be another case where resonance seems to be possible. 2 different ways, equal. In this case, they look pretty equally good, as it said on the other side. You know, when you have equal contributors, those are the same, like this. That is a thing that happens. For ammonium, here we go again. We're going to draw a nitrogen. I need a minute to draw our hydrogens. So we make bonds. And now we have a problem because this hydrogen's not good. Now what's great is that this plus means we can remove a hydrogen or an electron from wherever we want. And actually, just like we did before with the oxygen into the carbon in carbon monoxide, we're going to donate both electrons from the nitrogen to make that bond. And what we get is a structure that looks like this. And again, do not forget your brackets and your positive charge. Now, thiocyanate is the most interesting one here. I'm going to skip to the end a little bit. You can work through this yourself if you want to. The extra electron probably is going to fall into the nitrogen to make things work out. But 16 electron 3 atom systems look suspiciously to me like a carbon dioxide situation, which means we have 3 options. We can either have the double bond scenario. We can have the single bond triple bond scenario, or we can have the triple bond single bond scenario. Now this is far more interesting than the nitrite example because that's too many electrons. Because in this case, unlike with the nitrite, both sides of the polyatomic ion are not the same atom. So in the top case, we've got a double-double, single, triple, triple-single. But if we look at just like the sulfur, we have a double bonded, a single bonded, and a triple bonded. So we get to weigh out, like, which is better? A singly bonded sulfur and a triply bonded nitrogen? Which is better, which is worse? And to answer that, I want to take a look at formal charge. So here are our 3 structures, A, B, and C. If we can pull a little bit of information from before, a carbon with 4 bonds and 0 lone pairs has a formal charge of 0, and that speeds things up dramatically. For sulfur, just like oxygen, we have 6 valence electrons. We're going to subtract 6 for the lone electrons. Minus 1 is a -1 for our bonded right there. And then for our nitrogen, we have 5 electrons, minus 2 lone electrons, minus 3 bonds is 0. For this sulfur, we have 6 electrons, minus 4 lone electrons, minus 2 equals 0. And for the nitrogen, we have 5 minus 4 minus 2, and that's -1. And then finally, for this one, the sulfur ends up being 6 minus 2 minus 3 is a +1, and the nitrogen ends up being 5 minus 6 minus 1, which is actually -2. So in general, our evaluation for once the formal charge is written is that Lewis structures with minimized closest to 0 formal charge, not lowest as in most negative, are best. That said, I don't like structure C. Too much formal charge. There's a -2 and a +1. We've pushed electrons far too far to one side. Now between the structure A and structure B, we've got 1 -1 and 2 zeros. This is good. Now, does this mean there's an equal distribution or not? Since they are not the same element, we should look to something else to help us make a distinction. And what we're going to use is electronegativity. More negative formal charge to a higher electronegativity. Now, this is only in the case where you have a tie, right? Like where -1, 0, 0 and 0, 0, -1. Obviously, like, not letter C over there, that might be a really good idea. But I don't really want to, like, advocate that because the truth of the matter is it really isn't a terribly good idea. Now, let me check 1 second. And nitrogen has the higher electronegativity. So in this case, this is going to be the major form, a double-double. This one would be minor, and this one would be more minor. I don't know what the word is that in that case, more minor. So in general, formal charge is your way to evaluate what Lewis structures you've drawn and say whether or not they're valid beyond talking about octet rules and total number of electrons, because there are still some variations in there. And this gives you a tool to look at the quality of how possible that is to representing, in real life, how does this bonding work. Thanks for watching.